The previous video talked about what happens to the sampling distribution when we combine the sampling distribution of one proportion and look at the difference of another proportion, what happens to the sampling distribution. So if you're not clear on that, please watch that one. But here we're just going to go ahead and talk about the conditions to do any inference tests, whether it's a confidence interval or a sig test. We're going to actually construct some and then perform a significance test. So just a quick recap of the other video. When we combine the distribution of P1 and P2 and P2 minus P1, if we check for large counts and it works for P1, we can assume it's normal. We check large counts for P2, it's normal, then the distribution of P2 minus P1 is going to be normal. The distribution of a proportion is going to have its mean right in the middle, and that works out to be the same for the difference of them. So the mean, the center of the distribution of P2 minus P1 is going to be P2 minus P1. Whoops, a little mistake there. And then when we combine random variables, the variance, or how spread out it is affected, strangely enough, even though we're taking the difference, it's affected by the variance of the first one plus the variance of the second one. And that's what this part of the formula is, and that's what this part of the formula is. So we're adding the variance of P1 to the variance of P2, and then of course we have to take the square root of that sum to get our standard deviation. Here it is in. So here's the distribution of all the things that can happen when we take the difference between P1 and P2. The center is P1 minus P2. The sampling distribution is all the things that can happen. And the standard deviation, as I said, is the variance of P1 plus the variance of P2 square root to get the standard deviation. So maybe the visual helps you a little more. So confidence intervals always have the same basic formula. In this case, it's the statistic plus or minus the critical value times the standard deviation of the statistic. We're talking about proportions, so we're going to be looking at z's, and it's pretty straightforward how this is all going to work out, but you're going to use the same conditions that you've been using before. If your 10% condition is necessary because you're doing sampling, then you can go ahead, and it's met, you can go ahead and use the standard deviation formula, which that standard deviation formula, once again, is, in this case, the variance plus the variance, square root of that. They have to be met for both samples, and since this is proportions, we're looking at a critical z. When you're going to construct confidence intervals or run a significance test, you have to meet your conditions, and the conditions are the same conditions when you're dealing with one proportion as there is two. But the important thing is, and this is a lot of subnotation and such, but basically it's saying is check your conditions with both samples. It has to work for both samples, and once that's met, then you can go ahead and move on. Because we won't know the population parameters, we're going to go ahead and use our p-hats in our formula. So if we have our 10% meant, we can go ahead and use our standard deviation formula, which is the two variances added together and then the square root of that. Large counts means we can go ahead and assume that the distribution of P2 minus P1 is normal, and then we can just go ahead and move from there. So the statistic, when we're looking at the difference between two proportions, is that difference. The z is whatever we're talking about in terms of the percent level. Remember, 95% is 1.96, and 90% is 1.64, etc. And then here's our new standard error. So in general, a significance test is just asking you to look to see between two competing statements. Is it really a difference, or is it that difference can be explained away with the natural sampling distribution spread, or the random assignment of the particular treatments, for example. So an observed difference, when we're looking at the difference between two proportions, we want to know if that's going to reflect an actual difference in the parameters of interest, or if it's just due to chance. So significance tests help us to decide that. The null hypothesis has a general form, but now we're looking at the difference between two things, and we're always going to focus on the hypothesized value of 0. The idea that if the null is true, subtracting those two is going to get you 0. There's going to be no difference. What that means, of course, is if P1 minus P2 is 0, then we are assuming that they are the same. The alternative hypothesis is going to tell us what direction we think there might be, same like the rest of them. You know, it's either we think that the difference is going to be greater because one thing is going to cause something to be bigger, less than, or not equal to. We have the same 3 conditions that must be met, and they must be met on both samples. That's the key stuff. And I know it's tedious, but you got to check it on both samples. There's only one main thing that needs to be paid attention to that makes the significance test for this difference of proportions different than running a regular significance test. We always have to find our test statistic, that place in the distribution outside of which, or if it's a two-tailed test on both sides, that if it falls outside of that extreme, then we consider it statistically significant. In our particular case, when we're running a test statistic for the difference of two proportions, the statistic is going to be that difference. The parameter is always the assumption that we're having a difference of 0, and the standard deviation of the statistic is where things are going to be a little different. Because we're assuming that P1 is equal to P2, then we're going to go ahead in our standard deviation and we're going to pool the sample proportions. So we're going to go ahead and look at the original fraction that gives us the probability for P1, or the proportion of P1, and we're going to add it to the fraction for P2 as if it were a large probability moment, and that becomes our pooled or combined proportion. So let's say we had a statistic where in our first proportion we have 75 people said yes out of the 200 the 200 in our sample size. So that would give us a percentage of 0.375 or 37.5%. And let's say our P2 was 75 yeses out of 100. That would be 75%. To find our pooled, we have to go ahead and add the 75 plus the 75 and the 200 plus the 100 to get our new pooled. And so this one would be 150 out of 300, which is 50%. Now, you can't take the proportions and add them up and divide by 2 unless the end's the same number. You actually have to go and do this pooled situation. So once we've got it pooled, plug that pooled amount into our standard deviation part of the z statistic. You're going to be thinking to yourself, self, I don't want to plug numbers into this, so we're going to use the calculator, but you will need to know the original success and the n number to be able to plug it into the calculator. But this is what's going on with our z statistic when we're looking at the differences. So we're looking at a pooled, excuse me, proportion. P-value again, if we're talking about greater than, we're going to be looking at that tail. Less than, we're going to be looking at that tail. Not equal to, it's a two-tailed test, which is aligned with the equivalent confidence interval. And remember, if your p-value is less than whatever your alpha is, you reject. If the p-value is greater than, you fail to reject. So many important statistical results come from randomized experiments, but defining those parameters is a lot harder to do than just regular parameters, so we're going to practice that in class quite a bit. One of the things we need to remember is most experiments are used on recruited volunteers. Everyone in the population, that's largely unethical to just randomly choose people and randomly assign them to a treatment. So because of this, since the subjects are not randomly selected, we can't generalize or infer the results of the experiment to some larger population of interest, unless they have very similar qualities to the ones that volunteered. Researchers can draw cause and effect conclusions if the treatment was randomized, and since the experimental units are not normally randomly selected, we don't need to check the 10% condition when we're performing inference on an experiment. So this is what this whole thing says, and if you all decide that you want me to do a step-by-step on each of these, I will happily do that, but we're going to do that a lot in class.